Test. Testing, 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 testing. Testing, 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 testing. Let's see if we are live. Okay, I think we're live. Works. The volume does work. All right, we're ready to get started. Welcome to another Hupo stream. Today we are reading another paper. This time we're going a little bit into the bioengineering and biotechnology space. We're going to be reading a paper titled Deep Learning and Session-Specific Rapid Recalibration for Dynamic Hand Gesture Recognition from EMG. So this is a paper published just kind of towards the tail end of last year. Variety of different groups here publishing this paper. My alma mater, but then a variety of other schools such as University of Washington. So EMG stands for, what does EMG stand for? What does EMG stand for in biotech space? Human-computer interaction, HCI, dimensionality reduction, gesture recognition, encoder-decoder model, open hardware, and hand tracking. So, if EMG stands for electromyography. Electromyography. Electromyography is a technique used to measure and record the electrical activity of muscles. Okay, it involves placing small electrodes on the skin or overlying the muscle tissues. Okay, so basically they're going to be looking at the electrical signals coming out of, I guess, this device that we're going to read more about. And then they're going to try to use deep learning to classify these. So I thought it would be interesting to see how deep learning is used with this type of modality, like the signals coming out of an EMG, because I have not really seen what the state of the art looks like for that. So let's see. Read this abstract here. We anticipate wide adoption of wrist and forearm electromyographic EMG interface devices worn daily by the same user. This presents unique challenges that are not yet well addressed in the EMG literature, such as adapting for session-specific differences. Yep, this is definitely important. Also in the space of eye tracking for virtual reality. So eye tracking in virtual reality, where you can look at the position of the eye, is very sensitive to the positioning of the eye relative to the camera. So if you have a modern VR headset, usually they have kind of these calibration procedures that you have to do at the beginning of each session in order to calibrate your eye correctly. So I'd imagine maybe they have a similar type thing here for these EMG wrist devices. While learning a longer-term model for the specific user. Okay, so we have some kind of lifelong learning here. In this manuscript, we present two contributions towards this goal. First, we present misdirect. What a weird name here. Multi-session dynamic interaction recordings of EMG and kinematics. Okay, so it's a data set. A single participant performed 4 kinds of hand interaction tasks in virtual reality for 43 distinct sections. Okay, so 4 kinds of different interaction tasks. I think let's make that blue, which is the color that we use to highlight numbers, so quantitative things. 43 distinct sessions over 12 days, totaling 814 minutes. So not necessarily an absolutely massive data set, right? These are orders of magnitude of 10 and then orders of magnitude of 100 or 1,000. So it's not like a million hours. Analyze the data using a non-linear encoder-decoder for dimensionality reduction. Okay, so they're compressing or projecting this EMG data into a lower dimensional space with some kind of deep learning based architecture, I would assume. Small amount of a single session, performs at an accuracy of 79.5 as opposed to architectures which learn solely from the single session or learn only from the training data. Okay, so basically, it seems like the meat of this paper, or I guess the contribution of this paper, at least in terms of state of the art, is kind of going from this, right? Where if you try to perform this kind of classification task on only the data in your session, it's not going to perform as well as if you have their calibration, right? Keyword here, recalibrate. So there's some kind of specific calibration procedure that they've designed that allows you to tune the model, I guess, or maybe pick the right model, or we'll see exactly what's going on. Okay, recognition and use of hand behavior for control is a technique with a potential application in a wide variety of fields. Okay, so surgical, robotic, teleoperation, extended reality, virtual reality. EMG can be potentially transformative for HCI for consumer XR. Yeah, we do see in one of Meta's presentations, they had an EMG wearable, so Meta EMG. Yeah. So I think they acquired a specific company that does this, but it's basically a kind of like a wristband. Let's see if we can find a good image. Yeah, it's like a little wristband. And you wear this wristband, and then you can basically use your hand, and rather than tracking your hand by using computer vision and looking at the geometry of your hand and the position of your hand and stuff like that, it's literally reading the electrical signals that go into your hand. So it's a way to capture the hand without requiring computer vision, the current way that most hand tracking on VR headsets is done. An EMG wearable might enable muscle-controlled interactions, which could work around the limitations of optical hand tracking. So this is the computer vision-based hand tracking. 3 main goals must be met. Practical EMG signal acquisition hardware, a dataset to train a system or algorithm to make sense of the complexities, and an understanding of how user-specific and session-specific factors can be accounted for. Okay, proof of concept. I wonder if they're related to the company that Meta acquired. Publicly available data of simultaneous forearm and hand kinematic data. Okay, so they are releasing the data set that they collected, but this is going to just be a data set that like one guy collected in his room probably, so yeah, single subject, so it's not, ideally you'd have like dozens of people. Four main activities: unlabeled object stacking, unlabeled sequence of quick poses, and a labeled task of dynamic interaction gestures, and labeled task of rapidly performed poses. So I think unlabeled versus labeled here means that some parts of the data set are going to be labeled, like there's going to be a specific class label or a specific sequence of movements or gestures. But then you're also going to have just unlabeled data of this person just kind of maybe stacking blocks. Okay, and then the name they came up with for this data set is Direct, and they figured out a way to make it sound cool in the acronym. Second contribution is a classification scheme. The architecture learns session invariant features by training on a wide variety of sessions. Okay, so doesn't seem like they're doing anything specific. They're just kind of saying that the data set is general enough that it learns general features, but okay, encoder-decoder structure with a bottleneck layer. So this is a dimensionality reduction. Yeah. So whenever you're creating these latent spaces, right, these embedding spaces, another name for that, one thing that you're taking advantage of is that there seems to be an ability for information to get compressed and simplified in our universe, right? So you can take a higher dimensional space, compress it down to a lower dimensional space, and it seems like the neural networks are very good at figuring out how to compress the dimensionality of things, and then you can leverage the fact that the compressed representation that the neural network has created is actually quite useful and actually still contains a bunch of the information of the original higher dimensional space. So they're basically compressing the signals from this EMG data through a bottleneck, right, which is basically just a lower dimensional, like the width of the layer for that at the end of that neural net is smaller than the width at the beginning. That's what the bottleneck means. Background: acquisition of multi-channel forearm EMG. EMG is an integral tool for investigating muscle activation, neuron activity, and human control. So there's a couple different types of EMG. You have intramuscular or needle EMG by injecting a sensor into the tissue. That doesn't sound fun at all. Yeah, invasive procedures, discomfort, blah, blah, blah. Yeah, I feel like surface EMG is definitely the way to go. Okay, so whenever you see SEMG with a little s, that means surface EMG, which is basically just they have the electrodes that stick to you. Wet electrodes are applied to the skin with gel or paste. Or dry electrodes need no extra material. Yeah, I feel like if you have to like stick little glue things on to yourself, it's gonna suck. But if you have dry electrodes, that seems a little bit more doable. But the dry ones are prone to motion artifacts and are generally noisier. Okay, so you have wired or wireless. The wired ones are faster, but the wireless ones have a lag. EMG, you can create your own device. Okay, they have some examples of people creating their own devices, but you can also use commercial devices. One of the most commonly used devices is the Myo armband. So, coming out of Thalmic Labs. See that Myo armband. The Myo gesture control armband. So it is an SMG device. S because it's surface. You're not implanting electrodes. And then it's also dry. So these electrodes are dry. They do not require gel. And it seems like there's 1, 2, 3, 4, 5, maybe 8 different electrodes on this armband. So yeah, it has 8 SMG electrodes as well as an accelerometer, IMU, and a gyroscope. So accelerometers, IMUs, which is inertial measurement unit or inertial mass unit or something like that, and then gyroscopes. So accelerometers, IMUs, and gyroscopes, those are in your phone, and that's how your phone knows roughly what the position and velocity of the phone is, right? It knows whether your phone is flat or whether it's facing up. That's what the gyroscope does, and then the accelerometer is you can like flick your phone and it'll know that you're flicking it. So those sensors have actually gotten very good because of cell phone technology. Or because of the proliferation of cell phones. At this point, we have really good accelerometers, IMUs, and gyroscopes. So this Myo armband basically combines that. They take all the sensors in a cell phone, add the 8 SMG electrodes, and there you go. You got yourself a nice little EMG sensor. A market-dominant device or hardware standard may not have yet emerged. Okay, so interesting to see the authors of this paper, who are obviously experts in this space, saying that even though they used something like this, there doesn't seem to be a standout hardware manufacturer in the market, so we may yet see Meta make their own hardware. That could be an interesting outcome. Many publicly available datasets containing multi-channel recordings of hand pose exist. The most extensive is the Neenah Pro database. Okay. So here's another dataset here, the Neenah Pro database. Different factor, the number of subjects and sessions. Majority of the public available datasets contain static isometric poses. Okay, so there seems to be a difference between static hand pose and then dynamic gestures. Right, so much like in computer vision, this doing anything with images is very different than doing things with video. I'd imagine there's a similar dynamic here where doing things with static EMG data is very different than doing things with a time series of EMG data. Okay, so here are different data sets. So these are still pretty small, but I like this, right? 40 subjects, 44 subjects. That's a good amount of people. That's a lot of variety. Poses, these are all relatively similar. The fact that a bunch of these have 26 and 27, like, it makes me wonder if there's some standardized set of poses for hands. You have different frequencies here. It seems like 200 hertz is about what you can expect, but this one here, this is crazy. 5,210 hertz. That's significantly higher sampling rate, and a lot more channels too. And hand kinematics. Okay, so some of them also have ground truth data. Maybe not ground truth because you still have to run it through a pose detector, but they have a RGB camera, so you not only have the hand EMG data, but you also have the camera of what the hand gesture was going for. Algorithm trained on static poses may not be particularly useful because of realistically the user will make fluid and rapid dynamic movements in gesture interactions and must not be constrained to slow and discrete static poses. Yeah, so I mean, they're kind of arguing here that the static poses are no good, but I need no convincing. I am 100% with that. I feel like gesture recognition needs to have the time-based component. It's definitely not something you can analyze statically. Such as noise, that little typo. Most common types of feature extraction involve time domain calculations. So here you have root mean square, variance, and mean absolute value. So these are root mean square is basically a way to turn a trajectory into something that's a little bit easier to deal with. So new chat. What does root mean square what is the use of root mean square in time series data? Dimensionality reductions seek to facilitate by intelligently projecting the EMG signal into a lower number of dimensions. I like this way of describing a neural net is as an intelligent projector. Techniques technically predict. Have linear discriminant analysis, principal component analysis. These are kind of old school ways of doing dimensionality reduction. I think nowadays you would pretty much always use a neural net, especially if you have a data set. Root mean square is a statistical measure commonly used in time series analysis to quantify the overall variability or magnitude of a signal over time. It's defined as the square root of the mean of the squared values of a set of data. Okay, so you have the values of a set of data, which is the signals coming from each of these SEMG sensors, and you're taking the squared of those values so that they're basically not negative. Then you're taking the mean of those values, and then you're taking the square root of those values. So it gives you a kind of measure of how much variance there is, maybe how much noise, like roughly how much difference there is in the signal, right? Like how much does, for this individual little SEMG sensor, like how much does the value of it change over the time, over the individual sequence of it that you are now analyzing. Maximizing separability of group and capturing maximum variation directions. So what does this mean here? So these kind of like old school dimensionality reduction techniques, such as principal component analysis, or PCA, largely what they're doing is they're basically looking at your data, and they're trying to figure out which dimension has the highest variance. So there's a nice image to understand PCA. Yeah, this is like kind of the classic image that people use to understand PCA, but you have this two-dimensional data, this like kind of Gaussian and two-dimensional space, and the two dimensions you have are X and Y here. But what PCA can help you do is it can help you find these two dimensions, or these two dimensions here defined by these axes. And note how basically the dimension that it chose happens to be this line here, which is kind of the dimension in which there's the highest amount of variance, right? So PCA is good at finding those principal components, which are a sequence of p unit vectors, or you could think of it like a dimension in which there is a high amount of variance. Yeah, minimizes the average squared whatever, aka the distance between them, which is variance. Okay. Really, like, I feel like they have to do deep learning though, right? Are they just going to use PCA? That would be lame. Okay, the appeal of neural network approaches. Okay, here they are. They're setting it up. The technique. All right, training an architecture to reduce the input down to a few dimensions and then reconstruct the input from these dimensions. Okay, so they're basically just describing what an encoder and decoder does, right? You encode the data into a lower dimensional space, and then you decode it back into the original higher dimensional space, and then you can use that as a learning signal, right? Since you know the input and then the output, and then you can craft a loss function over that, and then you can train the encoder and the decoder. Recently, machine learning approaches have been used to recognize static poses and gestures by classifying EMG signals. Early studies used more classical approaches such as k-nearest neighbors and Bayesian classifiers. So these are old school machine learning techniques. The most popular type of machine learning architecture in this task is a CNN. They probably use a CNN over time, I would assume. Okay, no, they're using a CNN on spectrogram. So we saw this in the the audio synthesis paper that we read earlier, where basically with something like audio, which is actually very similar to this type of data, this SEMG data, right? It's just a signal over time. And what you can do is you can use Fourier transforms to turn that signal over time into a two-dimensional image known as a spectrogram. And then once you have that spectrogram, you can basically treat it as if it were an image and run it through a convnet. So that seems like a pretty good approach, or pretty standard approach to use for this type of data. But I'm curious if they actually do something a little bit more clever and they do something more specific to this problem. Okay, so they talk about RNNs, GRUs, and LSTMs. These are kind of old school sequence architectures. I think at this point, right, you would use transformers. None of these are popular at all anymore. Low, medium, high. Okay, so it seems like one of the things you're classifying is like kind of how hard the person is holding an object, right? So if they're like very lightly holding it, the signals coming into the armband aren't going to be super strong, and then kind of as you like flex your muscles harder, the signals will spike. Time series architectures are capable of recognizing gestures. Okay, so seems like they had a better approach with the GRUs and LSTMs than with the CNNs. I just really hope they use a transformer. I hope they don't use an LSTM. Intersession classification. Collected EMG data can differ drastically between subjects. The data may even differ between same sessions of the same individual. Yeah, prosthetic controllers to be highly subject specific. So whenever you see someone who has like a fake arm that can like they can control with their brain, it's like that the EMGs on that arm are like very, very specifically tuned for that person. So you could not take that arm and use it yourself. I wonder what the like calibration for prosthetics nowadays is like. Transfer learning. So maybe this is how you could get it to work across different subjects. Layer by layer element wise summation. That seems like a terrible way to do transfer learning. Showing significant improvement when implementing the adaptation. So they did a little bit of batch normalization. It's interesting how as soon as you go even just a little bit away from deep learning and machine learning research fields, and you go into kind of this, which is more biomedical stuff, like the approaches that they're using, right? The network architectures that they're using are almost like 4 or 5 years behind. So as soon as you leave the machine learning world, other people using machine learning are like 5 years behind. Retraining, which requires new data. Adaptive K nearest neighbor, architecture. It's not even an architecture, that's extremely old school. To align the distributions of latent representations from different sessions using generative models. So much of this work can basically also be applied to the reading of electrical signals from brain-computer interfaces, such as the Neuralink. It's a very similar type of problem. You have another work here. EMG signals used to perform the sequence are used to replace or update. In this manuscript, we take inspiration in the form of the hand dance. Okay, so this is kind of the calibration procedure, which is a representative sequence of motions that the user could repeat whenever recalibration is required. That's kind of cool. So basically you have a sequence of motions that you do with your hand, kind of like you're speaking sign language. And as long as that sequence of motions is like representative of the kind of broader set of all possible hand poses, then probably use that to calibrate. Okay, our data collection in virtual reality was developed in Unity. and designed to run on a standalone application on the MetaQuest 2. Okay, so these are pretty standard choices here. Unity is a game development application, but it's largely used for a ton of other things such as synthetic data, reinforcement learning, and any kind of VR application or system. Unity is really, really good for that. And then MetaQuest 2 is probably the best headset that there is right now. That's a pretty recent headset too, so this work is definitely fresh. We use the headset's built-in tracking to collect the hand's kinematic pose and present physically simulated hands to the user. Yeah, so the headset, the MetaQuest 2 does have built-in hand tracking, but it's doing it with the external camera. So there's cameras on the headset that are basically looking at your hands and then running a pose detection model. The high frame rate hand tracking mode was used, but our hand kinematic data is sampled with an average. Okay, so the MetaQuest 2 has a 60 hertz frequency for its hand tracking, so it's giving you 60 hand poses per second. And then the headset's display frame rate is 72, so it's a little bit of a discrepancy there, but it's close enough. So here we have the actual wristband, I guess, that they designed for this exact problem. 8-channel surface EMG device. So interesting that they decided to go for the same amount of EMG sensors as the Myo gesture control armband. Everything here looks 3D printed. Even the base here itself that this is hanging out on is 3D printed. Has a battery, a little microcontroller. They 3D printed the dry electrode. That's interesting. I wonder, there's no way that's made out of plastic, right? Probably made out of, here we go. Armbands electrodes are dry electrodes 3D printed from electrically conductive carbon black infused thermoplastic polyurethane. Okay, so the electrodes are printed, but the plastic that they use is electrically conductive. I didn't know that you could do that. I didn't know you could print electrically conductive plastic. That's interesting. I wonder how much better or how much worse that is than like an actual pure metal. So here they're describing, this is the chips that they use. This is a little bit more numbers here. 8 channels, 24-bit, 1000 hertz. And then it talks to a USB dongle. 1000 hertz, that's a lot, right? So you can definitely sample at a much higher frequency on these wristbands, right? 1000 hertz than you can on a headset, 60 hertz, right? So this could be a reason why we see these kind of wristbands used for hand tracking, is that right now, hand tracking on the Oculus Quest 2, for example, it's actually quite expensive to compute, right? So not only are you doing all the inside-out tracking for the VR headset, but you're also doing the hand tracking. So like there's a lot of stuff, that's a lot of compute that you're asking the Quest headset to do. It'd be nice if the Quest headset could just worry more about rendering the game and tracking the headset position rather than having to also track the hands. So if you can have your wristband or these little kind of EMG wristbands, and they do all the hand tracking, then it frees up a lot of compute on the VR headset to do more important things. Okay. Data collection. They collected it over 12 days, left-handed. Okay. Experimental procedures were approved by some regulatory agency to make sure nobody was being abused. Great. The 4 sessions here, you have hand dance, stacking, gestures, and dynamic interactions. The subject always began and ended with the hand dance, which was designed as a quick series of discrete hand gestures to warm up before and cool down after. Okay, so it's pseudo-random order, stacking, and interaction. So the hand dance is kind of like the start token and the end token of any kind of thing. Okay, so what is the stacking task? Stacking 3 times, 3 different heights, tall, medium, and short. Primitive objects were chosen, function-based objects more complex. Okay. Yeah, manipulation is actually quite complicated. I've done a bunch of manipulation and robotics work, and this type of stuff can get very complicated. So it seems like here they're just kind of doing very simple forms of it, right? Like close or open, but the kind of interactions object are extremely complicated in terms of like the position of each of your individual fingers relative to each other. So I don't think they get super deep into that. I think here it's basically just, can you tell if the hand is closed or like gripping or not gripping? So it's like the simplest form of manipulation, I think. So hand gestures, you have 20 different hand gestures here, given in a random order. 5 seconds, so little short hand gestures. These aren't very long things. It's basically just a classification problem where you're given 5 seconds of EMG data, and then you have to classify it as one of 20 hand gestures. So relatively simple task here. Okay, so here we have our first nice little figure here. I think it would have been nicer if they put these figures higher up in the paper. There's a lot of just kind of empty text, you know, like you want to make sure to have pictures in your paper so that people are visually attracted to your paper and want to read it. So you have different, I guess, objects here, and then you're going to be stacking them, and then depending on how tall the stacking height gets, all the stacking seems to be happening in VR. So you see here, you have VR. This is like a VR headset. What you're seeing from inside there, you see the hand. It's like stacking objects virtually. The 20 gestures for the in-air gesture task, with the idle pose being a representation of the general shape of the hand when subject rested. Note that for visualization, poses may not be in the orientation as they were when they were actually performed. Okay, so this is actually interesting too. Is your classifier robust to different orientations? So if I do a fist like this, I do a fist like this, is that going to be measured the same way? Yeah. Thumbs up, you have point, you have pinky, finger gun, victory, horns, shaka, I love you, little ring, 4, index flex, middle finger flex, idle, finger subduction, or finger adduction, finger thumb adduction, finger abduction 2, finger ADB thumb add, fist, wrist, wrist. Go. Pass the test. Dynamic interactions. The interaction gestures task. The subject performed a series of 14 dynamic hand gestures. Okay, so we had 20 static hand poses, and now we have 14 dynamic hand gestures. So total, we're at like 34 different classification categories here. Okay, so these are the hand gestures. So interaction gestures tasks. So you have a zoom, this. Have a nearer, asking the person to come near. Have a further, it's kind of the opposite of nearer. You have rest, fist loosed, fist hard, fist stiffened. So I guess this is the 3 different levels of flexing your grip. You have key grip, which is kind of thumb like this. You have pinch, pinch hard, pinch thumb, pinch index. You have basically each of the 4 Yeah, it's interesting to look at these and think about. I'm kind of a believer in long-term VR, and I think that eventually we will all be in VR headsets. And what is going to be the zoom and not zoom in VR, right? I think in kind of cell phones and tablets, we've kind of centered on kind of like this as the interacting, as kind of the gesture for zooming in and zooming out. But what's it going to be in VR? Is it going to be like this, like the full hand, kind of like they're saying, where you go like this and then like that? Or is it going to be two, like a pinch and grab, like that? Think about. Movements were based on modern mobile device smartphone gestures as well as actions we could believe to be useful. Yeah, this is like a whole area like of human-computer interaction that I think there's probably people that work on this, but kind of thinking about what the best gestures to use in a virtual 3D environment is. Because I don't think it's going to be the same as the gestures that you would use on a smartphone device. Okay, the classification. We're finally getting to the deep learning part. See what they do. Poses, blah, blah, blah. Okay, so they're basically doing a classification. We explore the time series capability of the bi-LSTM. So a bidirectional LSTM. Okay, this is kind of sad. I'm sad because LSTMs are very old. So, LSTM is long short-term memory. It's a type of neural network architecture that was originally designed for natural language processing, so text. And a bidirectional LSTM is an LSTM that doesn't just read a sentence from beginning to end. It reads it kind of the other way as well. So it goes from beginning to end and then end to beginning. So bi-LSTMs have like a little bit more context than LSTM, so they're going to do better, especially on something like this where you're trying to classify the entire sequence into one of 30 possible categories. The bidirectional LSTM is going to be better. But LSTMs are not really popular anymore. I think everyone in natural language processing uses transformers instead of LSTM. So, you know, these guys are biotech people. Like, they probably aren't like super up to date on their deep learning. So they ended up using this bi-LSTM, but I think it would have been a little bit better if they used a transformer a little bit more with the times. Yeah, like look at this. The architecture that they're using in this paper, like they're referencing a 2006 Jeffrey Hinton paper. Like that is ancient. That's like archaeology at this point in deep learning world. This architecture is not a true autoencoder. While this architecture aims to perform classification. Okay, the decoder is a mirror. So sometimes in this encoder-decoder paradigms, the decoder network is basically just the exact same thing as the encoder, just flipped. Hyperparameter was performed on a subset of 5 sessions. This is a very high training validation split. You know, like usually I feel like 90-10 is standard, but at 60-40 is a little bit intense. It's a lot of validation data. The approach found that 2 layers of bi-LSTM and 2 fully connected layers for each portion of the architecture provided the best performance. Yeah, so it's relatively small, so you basically only have here your 2. So this is the input. This is the 8 channels, so there's 8 lines here, each representing one of these little EMG sensors. So you have 8 sensors over 5 seconds, right? I think that's what it is. It's 5 seconds for one gesture. So this is each of those 8 sensors during the 5 seconds at whatever the frequency was think it was 60, right? 60 times per second. So that's the input. Then you're feeding it through these bidirectional LSTM layers. And then you have a fully connected layer, right? So just like a standard neurons connected to all neurons in the next layer. So this is like your standard deep learning layer. Then you have the output here. I don't know what this little chain means. Session calibrator architecture, which preserves, and then B, the main encoder decoder. What? Okay, so maybe they have like two different architectures here. They have like the encoder decoder, but then they also have like what they call the session calibrator. I don't know. They haven't introduced that yet. We'll see what that means. Here is your lower dimensional latent space. So we were talking about how when you take a high dimensional input and you project it into a lower dimensional space, that compression of information is a kind of a forcing function that makes your neural networks, the encoder here, learn an effective way to represent the information in this input, or an efficient way to represent that. So you're going from a 24/8 into a 1/4. And then the decoder is taking that 1/4 and trying to reproduce the exact input. But actually, they did say that they're not doing a reconstruction loss, right? So the decoder isn't taking the latent space or this embedding here and trying to recreate the input, right? So normally when you have an encoder decoder like this, you're doing a kind of a reconstruction loss where you're taking the output and then you're using and comparing it to the input, and they should be the same thing. But here, the decoder, they're outputting directly into the classification head. So there's 11 different gestures, and the output is basically the logits for each of those classes, right? So this is kind of your standard classification head here. So yeah, I mean, this is not like super well designed, to be honest. This seems like, again, the bi-LSTM is a little bit ancient at this point. Using an encoder decoder but not having a reconstruction loss is also a little bit sus. And I don't know exactly what this session calibrator stuff, why is it separate than this stuff? I don't know. Seems like a little bit sloppy. Okay. They got some dropout. They got Atom Optimizer with a learning rate of 0.1. That is huge. That's a big learning rate. Batch size of 128. Early stopping. Average of 20 epochs. This was not trained very long. Yeah. So these are very simple kind of numbers here. I guess they have a small data set, so like they kind of, you don't need to have a super big, super deep network that's been trained for a very long time with a very small learning rate, right? They have a very small network, a very small data set. So when you have a small network and a small data set, you train for a smaller amount of time and with a larger learning rate just so you can get it done quicker. But just looking from this, it seems like they could have gone, they could have put a lot more juice into the actual deep learning part of this research. Set of filters was applied. So they have a bandpass filter and then 2 notch filters. So what does a filter mean in this case? So this is the raw data that's coming from these EMGs here, right? Each of these little sensors here is producing one of these channels. So there's 8 sensors, so there's 8 channels. And that channel, right, it's going to be noisy, so you can probably see it, but it's kind of this noisy signal. So you can apply different filters that will clean out some of the noise in that signal. That's what they're doing. That's what they're describing here. And this stuff isn't new, right? Humans have been dealing with signals for close to 100 years now. So there's a lot of very good techniques and tricks that you can use to clean a signal that's noisy. So you have a low pass filter. Okay, so you have they removed a couple poses. Okay, here you have each session has 10 instances of each pose, resulting in around 500 to 600 samples for each pose per session. Each sample corresponds to a 8x24 window of the processed EMG data, which corresponds to a time window of 330 minutes. Is that minutes or is that milliseconds? It's probably milliseconds. What is 330 divided by 6? Yeah, so 330, that corresponds exactly to basically 5 seconds, which is what we saw earlier in the paper. Yeah, so train validation test split. So this is an interesting thing here. So for example, when you're doing video data, sometimes people will take a video and split it into frames and then split those frames randomly into train, test, and validation. But the problem that happens when you do that is that frame 99 might be in the train data set, then frame 100 might be in the test data set, and then frame 101 might be in the train data set. So what you're effectively doing is that your test data set and your train data set are basically the same. You're training on your test data set because you're taking frames from the same video. So there's a similar situation happening here where because you have this windowing, right, you have to be careful because consecutive samples will contain a portion of identical data. So if you just naively split into train, validation, test, why decode? Agreed. Okay, car split 80-20. Using random splits would introduce data leakage between training and testing sets. Yeah, this is important. So if you're doing anything with time series, be aware that you can't naively split your training and testing data. It is important. Okay, training and calibration. I think this is where they might explain this calibrator thing that they were doing here. To understand as every session is distinct, we propose different training schemes. For the cumulative and retraining schemes, we use the first 38 sessions as a training set, and then we use the last 5 sessions as a test set. I think that's a good way of solving this problem that they discussed here, right? Where you want to make sure not to naively split. So, example of a split, so a train test split. This ensures that split include equal example of poses and are not simply random selected. Okay, so basically you have a user, they're performing a bunch of different motions here, and you split it roughly 20% for testing, 80% for training, and it's split in such a way that you don't have you don't have things that are basically the same in both. So it's kind of a clever little splitting here. This is all kind of hand designed. Pun intended, I guess. Okay, so training over a large amount of data from a single user. They have 70, 10, 20 for the split. A cumulative scheme. A draw of machine learning is that architectures can take advantage of large amounts of data to learn hidden general relationships. To understand how much underlying commonalities exist between sessions, they split it differently. Okay. Okay, so they're doing different kinds of splits here depending on whether they are using a single session or multiple sessions. I don't know. I think they're getting a little bit caught up in just the training and testing split here and doing a bunch of unnecessary stuff. We imagine that a high-quality algorithm should be able to take advantage of large amounts of data as well as being generalized, as well as being able to generalize to specific sessions. A different training scheme is used to isolate the session-specific differences from the common relationships. A session calibrator architecture. Okay, here we go. They're finally describing the session calibrator here. Is shown in Figure 5a is trained and validated while the weights and parameters of the encoder-decoder architecture are frozen. Okay. So basically, then the encoder-decoder is frozen while session calibrator is frozen, and training is done again using the same data split. By first recalibrating the data from the specific session is transformed to not contain the irregularities of the session. Okay. So they're kind of doing this two-part training. They have what they're calling here the session calibrator, which is actually very similar. I think it's, if I remember from up here, it's you have fully connected layers, you have the bidirectional LSTM layers, and then it actually keeps the input and the output the same. So it's a 24/8 input, 24/8 output. So you can maybe roughly think of this as the feature encoder, right, or the backbone in a computer vision problem. So what they're doing is that they lock this encoder-decoder part, right? So they freeze the weights and then they push the gradients, I guess, all the way from here. So all the way from the classification loss here, and then they push them all the way back. So then they run this for some amount of time, and the session calibrator gets a bunch of gradients. The weights get updated here, and then they'll switch, and then they'll freeze the session calibrator or the feature encoder or whatever you want to call this, and then they'll push the gradients here. So I think the gradients are always coming from right to left, right? So they're coming from this classification loss, and then they're either going into the session calibrator or they're going into the encoder and decoder. Yeah, this just does not, this seems really weird. Like, I agree with you, Popo PK, like this two-step procedure here and like the unnecessary dimensionality reduction here does not seem like a necessarily good choice. This allows for the encoder-decoder to extract the underlying similarities, while recalibrating learns to transform the data by mitigating the effect of session differences. Okay, so I guess when they're pushing the gradients back, they're using different sessions. So basically what they're hoping is that this session calibrator learns some kind of way to make this 8-channel signal here a little bit less session specific. But I feel like you could have just taken this and then just put it as part of this architecture and it would have been fine. I don't think it needs to be its own separate part. Recalibration training scheme has the highest performance, while single session and cumulative have lower accuracy, so okay. Bifold cross-validation was performed twice. So they did a lot of K-fold cross-validation. So this is when you change your training and your validation and your testing splits, right? So basically you perform those splits many different times so that you are training on different subsets of your data and testing on different subsets of your data. And this is something that was more common previously. So whenever data sets were smaller and training didn't take as long, right? Before kind of the days of deep learning, this type of K-fold cross-validation, as it's called, was much more popular. But now that you have these absolutely massive data sets and you're training these extremely large neural networks and it costs a lot of money. Like, you don't really see this anymore. You don't really see k-fold cross-validation because it's just kind of too expensive to do, and it doesn't necessarily give you a very good, doesn't really make your stuff that much better. So like the type of stuff they're doing here, right? This 80-20 kind of splits, right? 60-40 splits with k-fold cross-validation. That is very like 2010 in terms of kind of the time period of machine learning. It's not very much 2020 stuff. Okay, so they have a confusion matrix, reveals that gestures within a group, like the first gestures or the finger dexterous movement, are more often misclassified as each other. The more forceful movements like the clenched fist and the hard pinch are also sometimes misclassified with each other. Yeah, so at the end of the day, right, this thing is just measuring the electrical signal coming from your muscles, so it doesn't necessarily know like the position very well, but it's just mostly reading how hard you're flexing your muscles. So if you have a fist and you're flexing your muscles really hard, it's very hard, or it's going to kind of misclassify that with just pinching your fingers hard. So it's the magnitude of the muscle flexion is really what it seems to be capable of measuring, not necessarily the position of your muscles. Or the position of your fingers, sorry. Single session scheme seems to show only a few main groupings. Okay, so we see here the confusion matrix. So basically what this is here on the X and Y axes, you have all the classes, right? So there's 14 different types of gestures. And then what you want to see ideally is something like this, where each gesture is very much or very strongly tied to itself, right? So whenever you have this diagonal with the confusion one means that this gesture almost never gets confused with any other gesture. It pretty much only ever gets labeled as itself, right? So this is what you want to see. You want to see a vertical line of ones and everything else 0. And they're showing you that when they do the recalibration, you do see that. But when you are using only a single session, you have a bunch of kind of misclassification here. So for example, here, the open hand is often misclassified as these things. So open hand is often misclassified as one of these, which makes sense because they're very, very similar. Here, I guess this is kind of like a tease knee or a PCA. So these are visualizations of the latent space. So the latent space is this, right? This little right here, this 1x4 lower dimensional latent space that your encoder and decoder are creating. You can actually plot that, and then you can see roughly where each of these gestures are. So you can see how all the green dots represent one specific gesture, and you can see how they're all kind of clustered together. All the blue dots represent a different gesture, and you can see how they're kind of clustered together. These type of dimensionality reduction visualizations are like generally not good. So honestly, like this is not good. These are not good charts. There's a reason you don't see these anymore. Like these were popular for a short period in the machine learning world where people would kind of show these plots, but it's actually very difficult to interpret these plots, right? And they can be misleading. So people have kind of moved away from these type of tease-knee plots or PCA plots. One of the motivations for comparing the 3 training schemes was to examine any potential benefit of using large amounts of data. It is found that there's benefit to using other sessions during training. Okay, suggesting that training on further data only provides only small incremental benefits. During recalibration training, we trained with a single session. Okay. Discussion. The enormous potential for EMG as an interface channel has been recognized for decades. It is a window into the activity of the body, muscles. Muscles are means by which human interacts with the world. By using EMG, we can make devices and systems that seamlessly mesh with those interactions. Yeah, I think long term too, this like EMG is the same technology that you're going to use for brain-computer interfaces, right? You're basically looking at the electrical signal that's coming out of your brain, right? Your the individual neurons in your brain. So being able to read and classify and understand the electrical signals that are going into like all throughout our body, I think is definitely a huge research direction. EMG signals reflect the dynamic physiological activity of muscles. Practical realizations are likely to be systems worn daily by the same user. It is not necessary to make a single model for all potential users if we can leverage the data arising from repeated use for a single user. Likely you'll have kind of a base model that's been trained on a ton of people, and then you'll have some fine-tuning for each specific user. We believe that for commercially viable XR interaction, quick and dynamic gestures are more common and natural to users. Architecture choice. The reasoning behind using the encoder-decoder architecture with a bottleneck layer comes from two factors. The first factor is that of visualization of the performance of each architecture. The latent dimension allows for low-dimensional representation of the data in which patterns cluster. Okay, so I mean, that's a terrible reason to do that. They're saying that the reason they used this encoder-decoder is so they could create this plot, but these plots are misleading, so I don't know about that. While pure performance metrics like accuracy or RMSE can be adequate to report overall performance, this latent representation affords the opportunity to better understand how an architecture may be learning or representing data. Yeah, I think that's a little bit of a weak justification. We are developing systems for using low-dimensional EMG control to interface with low-dimensional representations of high-dimensional virtual or prosthetic hands. Limitations and future work. Differences in data acquisition, number of gestures. There are diverse approaches to what EMG frequencies should be included. Okay, so even some of this filtering that they did isn't necessarily agreed upon. There seems to be a variety of different tricks here in terms of what ECG crosstalk. Most ACI, HCI applications use low frequency cutoffs. Interesting. So maybe different muscles and the size of your muscles maybe changes the frequency of the electrical signals that are traveling through your body. So by filtering different frequencies and having these like low pass, high pass filters, maybe you can filter out bigger muscles and only choose smaller muscles. I'm not sure. An interesting direction would be to test the effectiveness of the recalibration architecture by passing these transformed features into various other models. Yeah, I mean, there's other more interesting things. Do not implement these methods, architecture design choices, hyperparameter tuning. Yeah. I think they could have done this with a transformer and without this encoder-decoder framework. The more interesting problem to me is someone should do this with a transformer, but then figure out a unsupervised or self-supervised training objective, right? I think all the big successful models, machine learning models that you see nowadays are trained on these low dimensional, or not, are trained on unsupervised losses, right? So someone who can figure out some way to create an unsupervised or self-supervised training paradigm for this type of data, SEMG data, and then just run it on every single piece of data you can find. I think that would be a way to create a much richer and much more powerful embedding or feature encoder that creates latent vectors. Yeah, so increase the size of the data set is a huge thing that they can do. Apparently, electrode placement is critical to ensure signal quality. Interesting. EMG recordings from electrodes placed on the wrist often provide better quality for gestures than the forearm. This paper presents a dataset which a novel device design was used to collect, consisting of 4 distinct tasks, of which some were repeated, of varying dynamic hand movements and tasks. Quick sequence of poses back to back, a sequence of poses where each pose was repeated rapidly, a sequence of dynamic interaction gestures. This is all one sentence. That's a very long sentence. This dataset collected both EMG and hand kinematic data from hand tracking software. One of the largest continuous dynamics datasets publicly available. I mean, that's almost sad, you know? Like, to me, it's like, this just shows you how early the SEMG research world is, that the largest dataset is 13.5 hours of data. Like, imagine what would be possible with 1,000 hours of data or 10,000 hours of data and hundreds of subjects. Marked improvement over the single session. Okay. Future works will focus on utilizing the rest of the dataset for dynamic kinematic control through dimensionality reduction architectures. I think all forms of deep learning are a form of dimensionality reduction, so dimensionality reduction architectures is kind of a moot point. Cool. That was a nice little cute paper. So maybe just to summarize, basically this is gesture recognition, which is basically hand movements, right? And you're using this SEMG device, where S means surface because you're not actually putting electrodes into your skin. You're basically just touching. The interesting thing about this little device is that they actually 3D printed the electrodes. So the little electrodes that are contacting your skin are actually 3D printed. So the whole thing is basically 3D printed, obviously, except for the battery and the wire and the microchip. 8 channels, so there's 8 different electrodes on here. They collected a data set where someone did a bunch of different stacking and gestures, kind of static gestures, and then interaction, or not static, none of these are static. Each of them is like 5 seconds long, and then you have these different gestures. They never explained what the hand dance was, but so it's a classification problem. They have this somewhat complicated, unnecessarily complicated neural network architecture. They're using kind of an outdated by LSTM. They're using an encoder decoder in kind of not a good way. Like, because encoder decoders are used when you're using a reconstruction loss, but here they're not using a reconstruction loss. They take out the last head of the decoder and they just put a classification head on here. So this is a very weird architecture. And then they also have this additional kind of like mini feature encoder, which they're calling the session calibrator. and then they do this kind of two-part training where they freeze one part and then they freeze the other part, which is also a little bit weird. So very cool device, very cool technology, very good figures. I like these figures, but the deep learning is a little bit weird. I think they could have chosen better stuff, but they did release their data set, and you know, this is promising stuff. So this is other data sets that have been released. So it does seem like this one actually is the worst here, or the best. Here you go, Kazmarek. So this paper, 2019. So if you're doing work in this field, definitely check out these data sets here. Yeah, so that was that. Hope you guys found some of that interesting or useful. If not, I'm sorry, but thanks for watching and have a great day.